হ্যাঁ মহারাজ, আমরা এবারে লাইভ স্ট্রিমে যেতে পারি। হ্যাঁ, লাইভ হয়ে গেছি, আমরা লাইভ হয়ে গেছি। ঠিক আছে। হ্যালো এভরিওয়ান, ওয়েলকাম টু আওয়ার সেকেন্ড সেশন অফ ওয়ান ডে virtual seminar organized by Department of Chemistry, Ramkrishna Mission, Belur Vidyamandir. In their first seminar, we have two speakers, Professor Datta and Professor Indranil Partro, and we have a very wonderful talk and very nice discussion. In this session, we have with us Professor Indranil Chatterjee, who is one of my childhood friend, and we stay many years together and share many memories. But before that, I like to introduce him as a emerging scientist and as an emerging professor from IIT Ropar. He completed his BSc in 2006 from University of Calcutta, and then moved to IIT Kharagpur, where he completed his MSc in 2008. Then he completed his PhD from University of Munster in organic catalysis. Later on, he joined as a postdoc at Spain IC Institute named ICIQ, and later on the second postdoc he completed from University of Berlin in 2014. From 2016, he joined as a assistant professor at IIT Ropar. His area of research is asymmetric synthesis, design of asymmetric catalyst, new catalyst based on Lewis acid base characters, and he has published several journals, in fact very good journals, and have published even book chapters also. Recently, he also bagged the Best Teacher Award from the IIT Roper, and I really thank him for taking his time out to give a lecture to our college. I welcome Professor Indranil Chatterjee on behalf of our department and on behalf of our institution. Please, Indro, let's start your talk, and let's have a wonderful discussion on the organic chemistry.
Yeah, thank you, Professor Asa, and thank you to the whole department and Ramkrishna Mission for giving me this opportunity to talk about in this nice avenue. So today actually it will be like a teaching type seminar. So where mainly I will discuss about the asymmetric catalysis. Okay, so the talk will be majorly focused on how we can generate asymmetric center, how we can introduce chirality, what is the need and necessity for the chiral molecules, how they behave. Okay, and before that, so we'll introduce little bit of some terminology. Okay, so this is my research group. So it was in 2019. So now the group is little bit large, about 9 PhD students and 2 master students. Okay, so let's begin with some basic knowledge of chirality. So for example, asymmetric center. Okay, so throughout this discussion, actually I will discuss about mainly the chirality from carbon center, but it is not necessary that the carbon center it's only itself chiral, but there are heteroatoms that can also generate chirality. Okay, so the basic definition that an sp3 carbon center with 4 different group attached. So this is the necessity for asymmetric center. Optical activity. So the optical activity is that the ability to rotate the plane of the plane polarized light. So I will discuss little bit in details later. And the chiral compound, which compound actually that compound that is optically active. The achiral compounds are generally optically inactive and they will not rotate the plane of plane polarized light. And how we can measure this? We can measure this by using polarimeter. Okay. So stereoisomers. So what are the stereoisomers? That's compounds with same connectivity but different arrangement in space. And based on this, we can have 2 different other category, enantiomers and diastereomers. So what are enantiomers? The stereoisomer that are non-superimposable mirror image. So there must be mirror image relationship but the mirror images are non-superimposable. So generally, their optical rotation value can be different based on the chiral center or the chirality, but in general, the properties, the physical properties are very same. Whereas diastereomers, generally, they are not the mirror images, okay? And they can have different physical properties. So this is an example of plane polarized light. Okay, so I will discuss in details about what is going on throughout the polarimeter. So, okay, so this is a light source, this is a normal light, and this is the polarizer. Okay, and this is the direction of light propagation. So the plane polarized light, and here is generally the sample chamber. So here the sample dissolve in various solvents, okay, and the light is going like this throughout the sample chamber, and then this is the plane of polarized light, and you can see if the light has not rotated, okay, that's mean the molecule is achiral. Okay, so what will happen during chiral molecule? So if your molecule in the sample chamber it's chiral, it will rotate. So this is the direction of plane polarized light, and if the molecule is chiral, it will rotate the plane of the plane polarized light. You can see there is a deviation of angle. And this is another pictorial representation of polarimeter. So here is the light source, this is the polarizer, and this is the sample chamber. So here your sample chiral or achiral is dissolved in solution. Okay, and this is the analyzer, and then we can detect. And what is the outcome? The outcome is the specific rotation. Okay, so a specific rotation generally denoted by alpha divided by CL, or you can write also 100 alpha by CL based on the concentration. So alpha, what is alpha? Alpha is the observed rotation, what we observe after passing the light through polarimeter. C is generally the concentration in gram per milliliter, and if you can convert this gram per milliliter to milligram per milliliter, then you must multiply with 100. And length, L is the length of the tube in decimeter, and this is generally fixed for a single polarimeter. And then depending on the nature of the chiral center, you can have dextrorotatory, that is the clockwise or plus sign, or levorotatory, that is the anti-clockwise or minus sign, and that is the outcome of observed rotation, and then we can calculate the specific rotation. So again, a chiral molecule. So this is the carbon center, and you can have 4 different attachment around the sp3 carbon center, and these are the mirror image, and they must be non-superimposable. So before going to this, I will also like to describe few terms, because here actually mainly we will focus on how we can generate asymmetric center. Okay, so to generate asymmetric center, we need a prochiral center. Okay, so this is called a prochiral center, where if you replace one of the hydrogen by Z, okay, you can convert this molecule to a pair of enantiomer. Okay, so this 2 hydrogen of a prochiral center is called enantiotopy. Similarly, this is a carbonyl molecule, and this center of carbonyl, C center, is also a prochiral center. Okay, so here the chirality will come during take a simple example of reduction of carbonyl compound. So either the hydride reduction can come from the top face, or it come from the back side. Okay, so we can also generate another nomenclature for this prochiral carbonyl center. Okay, so if R1 has greater probability or greater advantage over R2, then we can have a clockwise rotation, O R1 R2, and we are denoting this rotation by assuming the nucleophile will come from the top face. So we have a clockwise rotation, and this is called reface. For any kind of nomenclature, we generally call R or S, but here for the carbonyl prochiral center, we generally denote with the reface. This is called rectus. And definitely, if the upside is reface, so definitely the opposite, like when the nucleophile will come from the backside, it will be C face, and that is the sinister. So very similar to the R and S nomenclature. So what are the diastereomers? So these are the example of diastereomers that generally do not have any mirror image relationships. Okay, and how to check the diastereomers? That must have enantiomer and plus extra chiral center. So this is the simple denotion. Let us take one example. Let us take one example that this these three molecule actually can, what are the relationship between these three molecules? Okay, so here you can see these alcohols in cis position, and the nomenclature is RR, and this is also cis position, nomenclature is SS. So that's mean they are mirror image but non-superimposable, and they are enantiomers. But when you have this molecule where the alcohols, the diols are in trans relationship, so that's mean they are, or even they are, a pair of diastereomers. Now, what actually, why this asymmetry or R and S centers are so much important? Okay, for example, you can see example of lactic acid, which is S lactic acid. You can easily find. Okay, the R isomer of the same lactic acid actually we can find from milk. Okay, so the source also different, and you can see the alpha value is just by changing the plus or minus sign. What else can happen? That the binding property of R enantiomer or S enantiomer can be different with the receptor. So here an example of R enantiomer that can bind with the receptor very nicely, but an S enantiomer, because of the arrangement, may not able to bind properly with the receptor. So you can see another example, thalidomide, R thalidomide and S thalidomide. The nature is also different. It is a sedative and hypnotic, and it used as a tetrazole. So this is also an example of amphetamine. So two enantiomers has two different effects. So this used as a stimulant, and this used as an adverse cardiovascular effect. So the properties, you can see not only that property, also the order. Okay, carbon. So this is the difference in chiral center, okay, of carbon. So this carbon having this chirality, it's a spearmint order. Okay, and this is a caraway order. Okay, so similarly aspartame. So this enantiomer, it is a sweet, but this is a bitter taste. And thalidomide we already described, it's a sedative hypnotic, and this enantiomer is a tetrazonic. So pharmaceuticals chemistry, actually in pharmaceutical industry, we actually need to have a number of enantiopure compound. Enantiomer and diastereomer may have adverse effects in pharmaceutical chemistry. Generally, to have the approval, we need a Food and Drug Authority approval to obtain the pure enantiomers. So another example, you can see that this is a penicillamine. Okay, so again, 2 enantiomer or penicillamine. This generally used for antidote in case of lead, gold, mercury, and whereas this enantiomer can cause optic atrophy, that is blindness. Okay, so different enantiomers can also have different either positive effect or negative effect that actually we do not want. Timolol, so this is a adrenergic blocker, but unfortunately this enantiomer are ineffective as we described previously, for example the receptor properties. And you can see that how much we need actually a pure enantiomeric compound or molecule in drug industry. Okay, so this is still a old data that how much the bulk enantiomeric drugs, how much cost, or how the industry invest the money to generate or to obtain a purely chiral molecule. Now the question is how to obtain. So again, as we started with the definition that we need a prochiral center, a prochiral substrate, then we can go on adding asymmetric center. It can be chemocatalysis, it can be biocatalysis. Also, we can have racemic compound. Racemic means chiral compound, but with no enantiomeric properties. Okay, so I will discuss also that later. So racemic compound, from racemic compound, we can also have diastomer crystallization, and we can have kinetic resolution, and that also can be chemically or enzymatic process. So the main purpose is to create single enantiomer. We have seen if we can have a pure R or pure S enantiomer of a molecule, then it can have huge effect either in drug industry, pharmaceuticals. Okay, so our target is to create a single enantiomer to control the stereochemistry at a remote site. The methods we'll discuss one by one. The resolution method that actually requires separation. It can have loss of materials. We can have chiral pool synthesis, and we can have asymmetric transformation, asymmetric induction. So for asymmetric induction to be practical, we must achieve greater than 99% enantiomeric excess. So that's mean either pure R enantiomer or pure S enantiomer. And the other target of an scientist is also that if we can develop methodology where we can changing the condition, the reagent, we can access both the enantiomer, either R or S enantiomer, both the transformation. The transformation should be very general, very simple. Control agent readily available. We do not require any extra steps. And more importantly, if we can generate catalysis. So what are the methods for obtaining enantio pure compound? Definitely, you can search in Google, or you can find many supplier that can actually supply purely chiral molecule. We can also isolate from natural product. We can have resolution technique, asymmetric transformation, and asymmetric induction. So what are the pros and cons of all the methods? We can purchase from commercial supplier, but the problem is whether the molecule we like to purchase, whether it's available or not, how costly the molecule is, and who will guarantee you that the molecule is pure. Although the company is giving you that it is a 99% purity, but who will assure you? So, and you know that based on this, there are to capture the market, there are a growing number of small companies. They can sell actually tailor-made specific chemicals, and this is also applicable to the industry. And you can have different contractors. So it's not a healthy process, I would say. Okay, but still, many people, many industry scientists, Academics also depends on the reputed company and to purchase from them. We can also isolate from natural sources. Okay. And if we can talk about natural sources, we can understand there are unlimited number of source, unlimited number of new structures. So the process is very tedious, very lengthy process. We need to find a perfect source, a proper source, and they must require vast amounts of purification, and then purification, then structural identification. It's a very tedious job, it's a very lengthy job. Okay, so and also remember that not all natural products are enantiopure, they can be racemic also. So that's mean it's a like trial and error method to identify the natural products, then purify them, structure determination. It's a very lengthy process. So other processes started directly from resolution. Okay, and one of the process is crystallization. So you can see this is again an industrial process for the production of menthol. Okay, through fractional crystallization. So what will happen? You can have metacresol, and that can convert to a racemic menthol. And if you remember that I mentioned already that it's a diastereomer, right? Racemic compound, that's a diastereomer. So what can happen? Diastereomers have the different physical properties. Okay, so we can distill by fractional distillation. We can isolate this diastereomer and this molecule. Okay, and then again what we can do, we can convert it to benzoate ester. And why to convert it to benzoate ester? To have a crystallization. So we can separately have the crystal of this molecule and separately have a crystal of this molecule. And the crystallization process is generally required to purify the molecule. Okay, and then what can happen? You can just hydrolyze the ester molecule, and you can get back a pure menthol of two different enantiomers. We can also have diastereomeric derivative formation. Okay, so this is a method actually developed long time ago by Professor E.J. Corey. Okay, so what you can convert, so this is a starting alcohol, so this is the alcohol. Okay, but it is a mixture of enantiomer. Okay, so you can convert this alcohol to ester. Okay, but this ester having a chiral center. Okay, so what can happen actually? This is a pair of diastereomers. Okay, and you can form actually one-to-one mixture of diastereomer. So previously what we did, we separate the diastereomer via fractional distillation, and also here actually we separate the diastereomer via column chromatography, and you isolate two different diastereomer, and then what you can do, you can just hydrolyze, okay, to obtain a pair of pure enantiomer. Okay, we can have chiral chromatography. Okay, so this is a technique but requires huge money. So we need a chiral stationary phase, a chiral mobile phase additive, then several application, analytical, preparative. The main problem is the price. And for a compound, we need to have a trial error using different columns. So the column should be available, should be cheap to obtain this methodology. It's a very costly methodology. So another target is a chiral pool synthesis. Okay, so chiral induction turns one stereocenter into many. So what is this technique actually? So you pick up a chiral molecule that you can easily find in nature, or you can buy even, you can synthesize even, but this is a small molecule. Okay, so this is deoxyribose. So you can see what are the molecules actually we need to use for chiral pool synthesis is generally readily available. Okay, and now what you can do, you have the fixed chiral center because this is a pure chiral molecule, and then you go on doing the total synthesis. Okay, and finally you can synthesize brevetoxin. Okay, it's a huge molecule, but based on the starting chiral molecule. So this is called chiral pool synthesis. You can again check what are the starting material. So this is diethyl tartarate. Okay, you can take this starting material after 12 step, you can synthesize this nicely chiral molecule. You can take carbohydrate that also readily available. You can extract carbohydrate, and after 17 step you can synthesize this natural product, which is a chiral molecule. You can use amino acids. So there are a lot of chiral amino acids that are naturally available. L-serine. You can go on synthesizing this small natural product having a chiral center or chirality that based on the chirality of L-serine. So very nice process. The advantage is that enantiomerically pure is a cheap source of chirality. So you can see all the chiral source should be enantiomerically pure, and it's a very cheap source. But what are the disadvantage? That you must have a pure enantiomer of the available starting material, and you need definitely, if you want to have this chiral starting material, you need to have performed some extra step. Okay, so asymmetric induction. Okay, so I will discuss about asymmetric induction again. This is an example of internal asymmetric induction. Okay, so again, internal asymmetric induction starting from a chiral starting material, which is a aspartic acid. Okay, and if you take this aspartic acid as a starting material, after several steps you can synthesize this natural product called vincamine. So the previous example was internal, and this is also an internal asymmetric induction, but it is a chelation control. Okay, so what do we want to do? So this is the chiral molecule. You have a chiral center here. Okay, and based on this chiral center, you can fix the nucleophile addition to this carbonyl compound. How? If we take boroacetate, okay, so this boroacetate as a hydride source, it can coordinate with this alcohol. Okay, and that is the chelation controls. Okay, and that actually gives the selectivity. So there are also very nice method. It's called asymmetric induction via relay catalysis. Okay, so what can happen here? I will discuss also this methodology that actually based on chiral auxiliary. Okay, so what is chiral auxiliary? That this is the part of carbonyl, and you form a amide bond. Okay, and you have a chiral molecule here, have a chiral center. Okay, so this is the auxiliary, and based on this auxiliary you can go on very simple transformation to introduce a methyl group, and later you can cleave this auxiliary so that you can have a aldehyde, you can have an aldehyde with a chiral center here. You can introduce a relay catalysis. So you introduce one time this auxiliary and you fix this chiral center, you introduce another auxiliary from here and go on synthesizing. After cleaving, you can generate this nicely chiral molecule. And this is another example of chiral auxiliary. You can see that this is the part we like to attach. It is a single enantiomer derived from S-valine. Okay, so again a natural source, a natural amino acid. And you can take this acryl chloride and you can form the amide bond. Okay, now this chiral center actually convert this dienophile to a single enantiomer. Okay, and then you have a achiral diene. Okay, and you can have single the simple 4+2 cycloaddition reaction that actually can generate after hydrolysis a chiral acid or ester molecule. Okay. You can generate also asymmetric induction via external asymmetric induction. So this is a very nice work by Professor Noyori, and you can see it's published in Science. Okay, so what is the specialty here? So you can see this is a organometallic compound, an organozinc compound, and this is an aldehyde. So you remember that aldehyde has a prochiral center. Okay, now how to guide the nucleophile addition? Okay, so this is a simple nucleophile addition to generate a chiral alcohol. But the question is how to guide this addition. And for this, actually, Professor Nauri used an amino alcohol, but in a catalytic amount. So what will happen? This amino alcohol, this is a purely chiral molecule. It will coordinate with zinc. It will coordinate with zinc, and then what will happen? The R group, the nucleophile, what will be transferred? It's under a chiral environment. Okay, and we can actually generate chirality by this methodology. And as I mentioned previously, our target should be catalysis. And this is a nice example where you can use this amino alcohol as a catalytic amount. So now what are the terms actually? Previously or many times it came that E. So what is E? E is enantiomeric excess. That's mean excess of one enantiomer. So for example, if we can generate 80% R enantiomer and 20% S enantiomer, the E must be 60%. Okay. So what is the E means 50-50? That's mean it must be, and 0% E, 0% E means it must be 50% R and 50% S, and that is actually the racemic compound. Now the question is how to determine the enantiomeric excess. Okay, so again, as I mentioned that enantiomers behave like a single molecules, whether it's a R or S, it generally appears as a single molecule, and it will give very similar NMR spectra for whether it is a R or it is an S compound. Okay, so what we need to convert the enantiomer to diastereomers. Okay, and for this actually generally people use Mozar's acid. Okay, so alpha methoxy, alpha trifluoromethyl phenyl acetic acid. So what will happen? This acid convert to the chloride or amide. Okay, and you can have a pair of diastereomer. Okay, suppose we'll do the reduction of carbonyl and we'll form alcohol, but the reaction we don't know what is the enantiomeric excess. Okay, so what we'll do, we convert this alcohol and react with this acid chloride starting from the Mozar's acid to a pair of diastereomers. Okay, and now diastereomers have different NMR spectra. Okay, and the advantage, not only the proton NMR spectra, the advantage of Mozart acid is also the 19F NMR spectra. From there, we can calculate the ratio of these diastereomers and this diastereomer, and from there actually we can tell about the enantiomeric excess of the alcohol. We can have also in many books you can see definitely that we can use various chiral shift reagent. Okay, so these are the example of chiral shift reagent, and European element also used as a chiral shift reagent, but these are always have some difficult tasks to use this chiral shift reagent. Okay, so the best methodology to use Cardal Hplc. Okay, so what is the Hplc does? So HPLC does, so suppose you can see this is a molecule. Okay, you have one, two, three chiral centers. Okay, you have three chiral centers. So if it is a racemic molecule, so what will happen? R enantiomer or S enantiomer, it can have different binding property. Okay, so by choosing the proper column, we can separate the R enantiomer and S enantiomer. And if it is a racemic compound, so that's mean you should have 50% R, 50% S. That's mean the E is 0. And you can see from the area of the peak, it is generally 1 to 1, 50-50. Okay, but this is a purely chiral molecule. I will not say fully pure, but mostly purely chiral molecule. And you can see one enantiomer, it has higher area than the other one. And from this, we can calculate the enantiomeric excess of the molecule. But how to judge whether it's R, S or R, whatever the configuration of the chiral center, we must need to do the absolute configuration using X-ray crystallography. Okay, so whenever we have the crystal structure, then only we can say this is this chiral center, this is S or R, only after the crystal structure. Or we can convert our obtained molecule to a known molecule. Okay, and to compare the literature, we can tell whether it's R enantiomer or S enantiomer. So how we can create again stereo centers from sp3 to sp3? That actually just we like to summarize that you can have a prochiral center, so we can replace one of the R1 to generate a pair of enantiomer. And similarly, this is again a prochiral center, and you must have a enantiotopic hydrogen. We can also use carbonyl molecules, and this is also a prochiral center, and the nucleophilic addition either from the top face or from the bottom face can generate a pair of enantiomer. Okay, so if the nucleophilic addition is not under a chiral environment, so what will happen? You will generate a mixture of racemic compound. Okay, so this is the chiral center, but the hydride transfer is not in a controlled fashion. Okay, so you can have 50% hydride can come from the top face, 50% can come from the bottom face. Okay, so you have 50% R, 50% S, and that's mean the E is 0. It's a racemic compound. Then what to do to generate chirality? So you can see this is a hydride source, lithium aluminum hydride, very well known. You can take this amino alcohol. This is called Darvon alcohol. Okay, and if you react this amino alcohol with lithium aluminum hydride, you generate this chiral hydride source. Now this hydride is under chiral environment, and you can do hydride transfer that can generate actually 70 to 80% enantiomeric excess. You can use also this kind of aminoborane catalyst, and here you can generate this borohydride, which is a chiral reducing agent, and this is a prochiral ketone. You can reduce using this catalyst to obtain up to 97% enantiomeric excess. Okay, so you can see this is the chair transition state actually, which will guide based on the large group or small group the hydride donation. So what are the other methodology? Other methodology for if you can have a sp2 center, so this is a double bond, you can reduce the double bond. If you reduce this double bond, you will generate a chiral center. Okay, and this is simply the hydrogenation. And this is the noble work from and Professor Noyori. Okay, this development of this hydrogenation protocol, right? So what can happen? You can generate in presence of ruthenium and chiral ligand. So these are binary ligand. You can have S binary or R binary. Is binary ligand and then coordinate with the ruthenium to generate R binary or S binary ruthenium complex. And it can undergo hydrogenation to form both the enantiomer. Okay, so if you remember the target for asymmetric induction, that we must have high asymmetric induction, 99%. By changing the ligand, we must approach we must access both the enantiomer. Okay, so this is a very nice work by Noyori. So what else we can do? So it is a really a never-ending process to describe the creation of chiral center. Okay, so you can have, if you have double bond here, you can do epoxidation and then you will generate a chiral center. You can do dihydroxylation. So you can have Saplex dihydroxylation, you can have Jacobson Katsuki epoxidation. So there are many number of examples to generate the chirality or chiral center. And this is also a very nice example where actually you can use catalysis. So the idea of the catalysis, what is the idea? It's a weak bond and strong bond. So what can happen? If you have a carbonyl, you react with a amine. You will form a iminium and that can convert to the enamine. Okay. And you know, if you remember the stock enamine synthesis, you can generate this enamine, then this enamine can react under chiral environment to install chirality at the alpha position. And what can happen when it reacts with the electrophile? It will generate iminium ion that can you easily hydrolyze. Okay, to leave or to get back the catalyst. And based on this methodology, actually, Hajos, Paris, Eder, Vickers, Sauer. So, although it's written 3 scientists' name, but it actually the synthesis involved the name of 5 scientists. 2 from another one group and 3 scientists from another group discovered similar type organocatalytic process using L-proline. Okay, so previously as I mentioned that we must need a secondary amine. So what are the natural source of secondary amine available is the L-proline. If you use L-proline, okay, you can generate a Robinson type annulation to form this molecule having 2 chiral center. And based on the acid use, you can either directly obtain this molecule or you can eliminate water to obtain this fused molecule having the chiral center here. Okay, so the advantage is that it's a natural source, natural chiral source. Okay, and there are a lot of other disadvantage also, but this is the beginning of organocatalytic process that actually avoid transition metal chemistry. Okay, so with this is really a never-ending process, but sometimes I have to end. And with this, actually, I like to thank again Swami Ekachittanando, HOD sir, Devashish Jana, and also my friend Professor Asadullah for giving me this opportunity to talk about the prospect of asymmetric catalysis. So I hope I'm able to I am able to make you understand that why we need chiral center, why we need to have different new methodology to generate chiral center. So thank you again for your kind attention. I'll be happy to answer your questions and query. Thank you.
Uh, Thank you, Indranil, for this nice talk. Let's have some discussion. Probably students ask something. So one of the students asked, during the final stage of hydrolysis to obtain a desired diastomer, can there be a possibility of molecule changing its back to another undesired diastomer?
Yeah, it can happen. It
What?
can happen. And it can happen whenever you have a complex molecule. For example, many chiral centers. Okay. So in that case, actually, if you can have more than 2 or 3 chiral centers, so this hydrolysis process can affect uh, your chiral centers. And also, uh, if your hydrolysis process involving base or acid, that can also, suppose you have a molecule that have a alpha hydrogen, okay, that is acidic alpha hydrogen, that also sometimes can affect and can cause epimerization. Okay, so there are many possibilities can happen. So we need to optimize this hydrolysis process to take a specific example.
Yes. So the next question is, I didn't get the question much. Anyway, see, can external, what is AI, AI be carried out with Gilman or Grignard reagent?
I think so. Yeah, it's known already literature. So it's a very simple. It's not only so zinc actually what Professor Nauri did. So he's mainly worked with the organo zinc compound, but you can use also organo magnesium or organo copper. But the idea is the same. These metals will coordinate with the amino alcohol, and then you can have a chiral environment.
In the chiral synthesis, we mostly use a chiral auxiliary.
Yeah.
The question is, are they all natural products more available in nature? If not, means they are asking means the chiral auxiliary are
Yeah.
mainly available in nature,
Not necessarily.
and if
Okay. So for example, you can see we already discussed about one example. Uh, I think we used Valine, if you remember.
even the glucose, you also use glucose as one of the example, I think.
Yeah. So many of them naturally available, or you can easily synthesize. Okay. I forget where is the example. We used actually chiral auxiliary from Valine, S Valine, which is a just a minute. Yeah, so this one.
I think you.
Yeah, you see, this is a chiral auxiliary. You can synthesize this chiral auxiliary from S-valine. Now, S-valine you can also obtain from amino acid. So this is an amino acid. So it not necessarily it will be available, but we can also synthesize.
Okay, it looks like we don't have any much more question, but I have one question to my friend, and
Yeah,
actually,
Ivan's
when I
auxiliary. Yeah.
teach, no, yeah, means when I teach them, especially amino acids and glucose, one question always my student ask, and sometimes I don't have answer. So I ask my expert now. So how the L amino acid in the primitive world, in the why the all the amino acids are S amino means L amino acids. So is there any I don't know means how it's happened then another question, how the first chirality generate actually. Uh, Means in the primitive world, when there is no chiral molecule, then how the first chiral center, like, do you have any idea, Indra? Can we discuss in this one?
Uh, Not properly actually. Uh, but yeah, it is difficult. I don't know because our mother nature can generate everything. So they are the chiral pool actually. Yeah.
Yeah, I
So
also don't know. Means I tell them sometimes, yes, it's still it's a good topic to research, but I don't know answer that.
yeah, it's a
How the
natural
nature
process.
all.
Yeah. Mm. So anyone if like to
Okay,
interest
Indra.
in chirality, I think so. This lecture mainly covered from Claydon, then little bit part of Jerry March, Smith, and if we really like to explore more, you can also have Jeffrey Obeck's book. Okay, so in for example auxiliary, so chiral auxiliary frequently used in total synthesis. So you can check in Jeffrey Obe's book, and that is a very nice book. Many chiral auxiliary you can have example, and you can see there are a lot of other example, even hydrogenation, epoxidation, hydroxylation, described very nicely.
Thank you, Indra, so much. Hello,
Yeah, your
hello.
voice is not. Yeah, yeah,
Thank you, Indra, so much. Hello. I'll ask my HOD, Professor Devasish Jana, to give a vote of thanks to all the participants and all the speakers for on behalf of the department and on behalf of our institution, Ramakrishna Mission Belur Vidya Mandir. I'll request Professor Jana or DJ sir to be provide a vote of thanks to Indranil and all the participants and all the speakers. Thank you, Indra, for this
yeah.
lovely
Thank you again
talk and so
for
much of
this kind
information.
invitation. Yeah,
Thank you so much.
thank you.
DJ sir, DJ sir, hello, hello, hello. Okay. It's look like DJ sir has some technical problem and some technical issue. So probably he's not connected through this. He was there initially. He was there. He connected, but somehow he lost. So I'll continue this vote of thanks on behalf of our Department of Chemistry and on behalf of our HOD. So thank you so much, Indra, and all the speakers. I like to thank and all the participants, and I like to thank our Jit Maharaj and Ramkrishna for make it happening in the virtual mode because in this pandemic situation, it's not possible right now. But as soon as the situation is over, I really want to invite all the speakers by person, and I want them to visit our institution, this lovely and beautiful institution, once at least once in a year, so that we have interaction. We have interaction with students, and speaker can easily interact with students, and students can be freely interacted with the speakers. So I, on behalf of our department and the institution, I like to thank our principal Maharaji, Ekachittanandaji, and our vice principal Maharaji to allow this platform to be happened. And thank you everyone to make it happen. Thank you so much. So this
Yeah,
session is over by
thank you,
now,
Varsha.
and the one-day seminar is over by now. So we'll send the feedback link to the registered participant only, and we are requesting the participant to fill the feedback form by tomorrow 5 p.m. so that we'll send the e-certificate to you to you by email, and that's it. We are over by now. So we'll send the certificate by email. Thank you, Indra. Thank you
Okay.
so much.